He was pretty good, wasn't he? We'll do a few more of his videos when we get to some of the other data structures. It's a shame he quit posting because he explains things well, and he explains them slightly differently than I do, which means you get to hear it two different ways. So we have an algorithm. I'm going to just write in the code that doesn't exist here. How would we determine what the order of that particular algorithm is? Anybody want to take a shot at that? If you do, put your hand up. Move to the top of the list and I'll call on you. Nobody wants to volunteer to be the first speaker tonight, or guest speaker? Okay, well let's look at it for a second and think about what we have to do.
What takes the longest?
The algorithm itself has that for statement, which, depending on the language you're working in, has some sort of complexity even to the statement itself. We can assume, and I intentionally didn't write it in formal code, that that's going to be the normal three pieces of something that iterates through another element. And so we would say I is equal to 0. And then we said if I is greater or equal to A, then we want to do something. Else, we want to be done with the particular item. And after we've done something here, we would insert an I++. Again, we're not using formal language here. We're just representing code. We could think of this as being a single primitive operation. We could think of what's going on in here as being a single primitive operation. The calling of this function depends on how many elements are in the thing, how many basic functions. Let's assume for a second that it does 30 items when we call it. This happens 30 times. If we're going to, not 30 times. It happens the number of times we get into this true thing where we're greater or equal than A. And otherwise, we're done. So we could go through and we could routinely or even laboriously count the primitive operations. There's one here, one here. We know the line itself had the original assignment, which is 1. It had the test, which it makes it 2. And then if it did do something, we had 30 items. That's 32 times somewhere near the A value, whatever A is. And A is really in disguise right now. And because of that, we have one time where when we're done, we don't repeat all that. So we've got that. We're going to come up with an equation that's going to look something like 32n plus 3. And then we're trying to figure out what the big O or the order of this particular operation is. So it's O 32n plus 3. Now who wants to describe to me what we can get rid of, what we have to keep, and all that sort of stuff? Surya, why don't you explain to me?
So the significant factor in this equation, this formula 32n plus 3 is the n, because that is what determines how this increases through time. So that's O of n complexity.
Okay. So basically what we know about the order n type of equation is we're going to look to see if there are any terms which have smaller value in the formula. So this is really 3 times n to the 0. 32 then itself, if we're left with this guy simply being 32n, 32 times a big number and a big number, they're the same thing. So except for where we'd be looking for performance, the order of this equation is on the order of n times, dependent on the size of the data. Now, if I take a bunch of data, I'm just going to call it a bunch for now. We'll pretend like this is some data structure. I'll just call it a DS for now. What is the order of me going through all the items? For instance, I'm going to print all the items. What sort of algorithm order does the print give us in that case? Oops. I'm going to have to log off and back on. My screen just went blank. I'll be right back.
I would have said it was a little linear, but not.
Okay, hopefully that won't happen again. Give me a green circle if you can hear me. Okay, and the question at hand is, what is the order of going through all the items? John?
Just n, the number of items.
So it's big O-N. Where am I typing? Let me put my cursor on that screen. Can it be any better than that? Miguel?
I think O1 is the best that you could do.
Constant would be, but can I present you every item in a list, or for example, in constant time?
Can you? I don't think so, maybe.
Yeah, that's right. You can. By the way, do you go by Mikkel or Michael?
Mikhail.
Mikkel, good. I got it right then. I am terrible with names, and I've been getting most of them right this year. Okay, so if we have a list of items, the best I can do is going to be big O-N. That means incumbent in us doing an algorithm for our data structure, if we include something that touches all the items, we can't do any better than big O-N. And we want to keep that in mind because we want our algorithm, at least the interface methods that we make available in our data structure, to run in better than big O-N time if possible. We want constant time where possible, and we're going to strive for that and see where we get. We'll see how good we can actually do. Now, it turns out that if you use the algorithms themselves and the data structure members to look at all the items, you yourself will cause it to be done in times at best. Maybe a lot worse than that, but at best, it could be that. We had a young lady that was in my elementary school when I went to elementary school, and we were just learning how to look up words in the dictionary. And she apparently didn't really understand how it worked. And so every time the teacher would give a new word to look up, she would always go to the very first page of the dictionary and drag her finger down the page looking for the word. Then she'd go to the second page. Then she'd go to the third page. And by the time she got to about page 100, she'd probably stumble across the word. Everybody else just alphabetically knew that it would be in the letter. So if it started with an N, go to the section marked N. And within that, it's alphabetized. She didn't quite get that. So a misuse of a data structure, we can't protect you against it. You can make the worst or the best case worse, but you can't make the best case any better than we can do. Maybe it's a different algorithm, but if I'm going to give you every item in a box, you've got to touch every item. And because of that, ON will be the type of thing we're going to be looking for. Does everybody understand that? Okay, now we're going to actually start in a strange place for an algorithms class, although it isn't really. We're going to start and we're going to implement an array. Java has arrays with the square brackets. When we're writing programs that are data structure specific, we're not going to use the square bracket notation. Instead, we're going to develop, and you've already seen the code for, an interface called iArray, which is specialized on some data type. I'll just put a T in there for now. So what we need to do in developing this is we need to understand what methods we would need in order to use an array. Are there any special circumstances involved in using an array? And later, as we start to learn other data structures, when would we prefer an array over some other type of data structure? So just out of the box, let me give you a couple of facts about an array, and ours being implemented as an iArray will take advantage of this. One of the things is, an array can't change its size after creation. Very important fact. I tell you an array has 4 items in it. It always has 4 items in it. It can't have 3, it can't have 10. Now we'll learn how to take an array and turn it into a resizable array, but that's a different data structure. Or something called a vector, which is another type of, same thing as a resizable array, but it does some of it automatically for you. So keep that in mind. Some other data structures will be very good about being able to change their size. So if you had a problem where you knew the amount of data, some of the other advantages of an array might get you to choose it because of the fact, once you set its size, you don't have to worry about it changing. A second item is all of the buckets in an array contain valid data. There's no such thing as having an index into an array at which there is no data. Now we could invent ways that we could make an array that's the case, but that's not this data structure. That would be a different data structure. For example, we could build an array that didn't allow nulls, and when we could just mark every place that we wanted to be empty with a null. But the array we're talking about follows these 2 rules. It can't change its size, and all of the buckets inside are initialized. They may be able to be changed, but they always contain some form of valid data. There's nothing in the bucket that says this data is invalid. Any questions about those 2 points? Do you understand those 2 points? Okay, now in Java,
He said no.
an unfortunate thing that we have is we can't indicate the constructors in an interface. And that's unfortunate. Because one of the things we're going to have to do is, because an array cannot exist without having a size, we can't initialize it and then have you set the size afterwards. It has to be initialized in its constructor. So as part of the notes in the documentation we would write, we would have to tell anybody that implements our interface that they minimally have to include a constructor that takes a size. Now, it might take other things like what are the initial values, but we're going to require that they give us one that takes a size. So even though we can't put it in the IRA, we know there's going to be a constructor that takes the size. Now, let's assume we have constructed an array. The array itself lives in memory one item after the other. So let's assume everything begins on an address of 4. It's a length of 4. This would be 0. This address would be 4. This would be 8. This would be decimal 12. This would be decimal 16. And in here would be the primitive data for an integer, for example, or the primitive data for a float, because each of those are 32 bits long. We also could have an array I don't mean for them to get smaller, it's just my pen is doing that. Or maybe we're on 2-byte boundaries. So we need 32-bit elements in here. These could be things like ints. They could be floats. A byte's 8 bits long. 4 times 8 is 32. So each of these is 32 bits long. Each of these would be 16 bits long. What type of data in the Java set of things we have could we stuff into this array? Raise your hand if you know. We went over it last time. Xavier?
Characters?
Say again?
Characters?
Character would be able to go in there. Yes, it would. Anything else? John?
A Boolean?
Well, a Boolean will be 1 bit, so it's probably going to be stored in some way that's hidden from us. So 16 would just be an arbitrary value for that. What other type of integral type is 16 bits? Remember, characters are unsigned and contain Unicode. A short. So a short is a 16-bit integer. It can contain a value from 0 to 65,535. Or if you wanted to see it the other way, since it's a signed number, it could be from 0 to 65,535 or down to minus 65,536. But they can be stored in here. One of the things, and I'm talking about primitives right now, one of the things that's convenient about this is, since I know the width of the character, I know this is index 0, I know this is index 1, I know this is 2, this is 3, this is 4. In order to find any piece of data, I simply take the index I want and multiply it times the size of a bucket, and I'll find the correct bucket. Same thing down here. If I wanted the 0, 1, 2 bucket, the third bucket, which is numbered index 2, I can simply take 2 times the 2 bytes, would give me 4, and I would find that bucket. So an array, let me actually put it on the other list over here, because it's an advantage. They have direct access to the items. I'll put here, if you know the index. So there's another thing that you might care about. You want to be able to get to an item in a list quickly. If you have some way of knowing what the index is, you get there in constant time. So those are some elements that we might be concerned with. Now, if these were not primitive, if they were, reference types, see if I can do this. I'm going to try to put these in a row without having to draw them. If this is index 0, this is index 1, index 2, index 3, index 4, whatever the size of these are, they will be appropriately sized. So if you multiply the index times the size, you find that element in the array. For reference types, the data is not really in the bucket. What's in the bucket is a reference pointer to somewhere where the memory or where the data actually is. Oops, I didn't want to do that, but there we go. We got a big fat box now. And the data itself is over here. Reference to it. Reference to the box. And the data is really here. Now, in the case of reference variables, these are always a fixed width because all references on a particular machine are the same size. We'll pretend like they're 32 bits wide, in which case we have a reference that points at the data. We won't worry about this extra indirection. We'll just assume that if we found this reference, it knows how to dereference it for us. Let's just be aware that that could be an issue. See if I can get rid of the big fat typing that's going on here. There we go. So if we built an array, what would be some types of methods? Because remember, the first principle of object-oriented programming is data abstraction, meaning there's a natural interface for a particular type. What would be some methods we would expect to see on an array? Kyle?
A method to call a particular index?
Okay, well, let's give that a name. You mean to get one?
Yes, like a get or a set.
Get something to do?
I guess both, a get
Okay.
and a set.
Okay, so we probably are going to have some sort of method that we'll call get, and possibly a method called set. Both of those need to have some sort of access to the data. So my guess is the get is going to need to be passed in the index, and it will return to us an item of that data type. A set method, more than likely, will take an index and something of the data type and probably just return void, won't return anything. So basically it does the equivalent, which in Java would be if you said something like x is equal to b sub 3. Or for a set down here, you might say b sub 4 is equal to 23. So we'll replace this notation with a call to a get with an index, returning a type, or the data element, and we'll be able to set the element with a 2-parameter call, one which is the index we want to change and the data we want to put there. Can you think of any other methods we would probably want to have for our interface? John?
Maybe get the length of the array.
Yeah.
Yeah, and we'll kind of standardize on that, and what we'll do is we'll call it, we'll get back an integer, and we'll use a word called get size. Now, For some data types, we're going to be able to ask the question, is the data type or is it empty, which would be true if size were equal to 0. But since even if we allow them to put a 0-sized array, if we construct one for them and there's no elements in it, it's not really empty. And since we don't have any way to remove things, we're certainly not going to have any remove methods because we don't have anything to replace it with. So those three are probably ones that we're going to need to have in our interface. Now, because we're going to eventually have to extend object, our interface doesn't extend it, but our actual implementation will. Let's go look up. Oops, it's the wrong class. It's this class. And I don't want that at all. I want this. On Java Lang object. This off to the side here. Okay, we will get a clone method from object. It is written in object so as to, I believe, throw an exception saying this object's not clonable. Yeah, clone not supported, which we want. If we want to override clone, we'll do it locally. Right now, we have no motive to do so. Equals will be able to be overridden for our array, the object itself, to see if it's equal or not. We may decide to put that in later. Initially, we'll go with if it happens to be the same object, it's equal. If not, it could be a separate array with the same values in it. So overriding it to collapse that and become a value type doesn't make a lot of sense. Finalize is deprecated. We don't need it anymore. It used to be run before Java was shut down, but sometimes Java was not shut down. It was just terminated. And so unlike a destructor in C++, where there's a little cleanup done for you, and it's more predictable, finalize never really worked right. Get class will do the right thing. Hash code for our purposes now will do the right thing. Notify all, those will do the right thing. We might, although I think for an array, we won't bother overriding the toString method. We our list down here. We might override toString. Make debugging easier. We don't need to do any of the weights, and that's all the stuff that object gives us. So probably the most we'll do is toString. There are a couple other methods in the interface that we're going to want to do as well. One of the things is, so that we play well with functional programming, we're going to want our interface to override another interface, which is called iterable. And of course, iterable is iterable on the type. Now, if we do that, find iterable. Oops. Oh, there it is, able. We're going to get an implementation of for each for free, which means we can self-iterate the array. We also can get an iterator and we can get a splitterator. A splitterator is used when you want to do functional programming with multiple processors and you want to iterate everything, but you want to get back multiple streams of data instead of a single one. And you can assemble them all back together at the end. So I'll probably provide you with a method for getting a split iterator, and probably, although it's not listed right here, I'll give you a default method as well, which will allow us to get a stream or a parallel stream out directly so that we can play well with functional programming. And right now, I think that would be hard for you to do. And so once you've seen me do it a couple times, then it won't be, but I'll probably supply those so that they're fairly straightforward. So that gives us some things. So we're going to be iterable, and as part of being iterable, we have to provide an iterator method, a split iterator method. We're going to get for free, what was the one I said there? We'll get for free a for each, and then we'll make sure we have a stream method and a parallel stream method in order to return those so we can do functional programming with them, or at least stream programming. Does everything I've been talking about make sort of sense? It doesn't have to make 100% sense yet because you haven't been through this at all before.
Yes.
Okay. So if we go to Eclipse and open it up, in the last class, after much bungling around, I managed to give you the right thing to load in order to get the interface for iArray in the correct directory. So let's all verify that we have that in the right place. If you missed the last class or something, you'll have to get it done. So in the project we're calling data structures, we have a source directory. We added an iFace for interface. We added an impl for implementation and a test for test files. We're going to go to the iFace directory in which we created a package, edu.mccc.cos210.ds. And in there we have the code for the iArray interface. Now, I mentioned to you very quickly last time that in general, when we have an assignment or we create a variable, if it's one of our types, on the left-hand side of the equal sign where the variable is named, it will be of type whatever the interface is. On the right-hand side, we'll actually create one that is of an implementation type. So we could have multiple implementations for the same interface and swap them in and out within a program, and the program should continue to work. It also means that if somebody writes clunky interface code and adds extra methods, we can't accidentally use them. So let's say I assigned all of you, I want you to write the implementation of array. It'll implement iArray. Well, you go out and write it, but a couple of you decide to add an empty method. In order for that to be prevented from being used, as long as we originally created in our minds as being an iArray, that method doesn't exist, even though it may be public inside of an implementation method. And that way you could test Joe's code and you wouldn't have to worry about he added extra things that you shouldn't be testing, or you write your code based on something he did, and of course it won't work with my test code. So here's our interface written out. We're going to give a package. We're going to say we're an interface called iArray, specialized on type T. That way we can pass any reference type to an array. We extend, interfaces extend other interfaces. They don't implement anything. Java, Lang, iterable, which is specialized also on T. We're going to have three main public methods. A get method that returns T, being passed in an index. I think that's the way we described it. One called set that returns nothing. It takes in an index and the data to be stored, and the ability to get the size. Now we're going to override the method that's inside of the interface iterable for the method splitterator. I'm sorry, it returns a splitterator. Its name is splitterator. And we're simply going to call within the splitterators with an S, it's a utility class, this general purpose method that gets our own iterator, gets our size, and then tells the world that we're ordered. By making sure that we tell it is ordered, when we're using streams, particularly parallel streams, our data won't get put out of order if we work on it from different streams when we recombine things. So it's important to tell it that if you are ordered. Now we also build two default methods, which simply return from stream support a stream past a splitterator, and whether we want it to be non-multi-threaded or parallel threaded. By doing that, that'll allow us to participate fully in the methods that are inside of declarative programming streaming portions. Now, of course, there'll be things there we can't do. For instance, if they have a to-list method, we can't use it because it'll turn it into the wrong type of list. Or if there's something that turns it into an array, they'll be turning it into a square bracket array, and we need it to turn it into ours. So we would have to rewrite or write for the first time methods that do those things, which is great. We want to write code. We want to become smarter than we are today, every day. And that basically describes the interface that we need to be an array. Hopefully it's complete. We'll find out if it's not. So what we need to do now is create an implementation of each of those pieces. So we downloaded some impl code in a different package. Package here is edu mccc cos210.ds.impl. Notice this didn't say .iface. It could have, but it doesn't. It's the main code, so it usually doesn't. But this is .impl. And here we have something. Notice that the name of the actual implementation in this case is the same as the interface without the I in front of it. So let's open that up and take a look. Why don't you quickly run your eyeballs, if you haven't yet, down that code, and then we'll talk about it. Take about a minute and a half here to take a look at it yourself. Make sure you understand it or could read it on your own. Okay, let's take a path through this thing. We're a public class called array specialized on T. We're going to implement the iArray class specialized on T, which means we additionally implement the iterable class because this guy extends that. Now our private data is going to be an array list. This is the Java array list, specialized on T. We're going to call it the array, and it'll have no value when we start. Now, we're going to use the Java array list as the place where we store our array elements. It turns out that array list itself is simply sitting on top of a square bracket array. So indirectly, we're avoiding any errors we would get from trying to mix array data with reference data. So this is a rare use of one of the Java classes inside of our implementation. Now, here's this required constructor. We're passing in the size. So we will create the array by creating a new array list of that size. Now, if we go look at array list, we'll find out that array list is resizable and it has all sorts of fancy features and things that we don't need. So as long as we're making ourselves contain the array, notice we didn't extend it, we contain it. We can control the access to the methods inside of it. So we only leak out and expose things we want it to do. It doesn't matter that it's more powerful than we need it to be. Very important concept. So what are we going to do? Well, once we have initialized it, we're going to go through it and we're going to set every element in it equal to null. Now, the array contains size, number of buckets. Every bucket contains the null, and the null is considered valid data until we put something else there. We could have in the implementation, but what wasn't required by the interface, we could have written a method which not only set the size, but set all of the data items to values. That sounds like a great test question for somebody someday. So you might say, well, we don't have that constructor now, but it would be really easy to add that. And we'll talk about that at a different time. We're not going to supply it as part of the base implementation. This is one of many implementations, though. This is our first implementation. We're going to override get. In order to do a get, all we do is we take the array called get, passing it the index, and it will return the data that was stored in the array list at that index. So that's a good implementation of that method. Very simple. Set returns nothing, takes an index and a piece of data. It goes to the array and sets at the index that piece of data. Exactly what we described it as needing to do. Anybody have any questions about those two methods? Okay, get size. Get size simply goes to the array and pulls out the size. So that sounds like that's a pretty good thing. It's always practically done for us. What order does that run in? That method. Actually, should highlight the next line up. It's order what? John? Didn't sound like John.
Big O1.
Right. Constant time. How about the set? Raise your hand before you speak. John, you already got one right. Mikkel?
Also big O1.
Yeah, it's also constant time. It doesn't matter how big the array is. It's going to multiply the index times the size of the elements, go there and return that item. It's not dependent on the size of the data at all. How about get size? Banoob?
Oh,
Big O-N.
Why would it be n?
Because it's dependent on the size of the data.
Well, it's going to return a value which is equal to the size.
like
As long as we keep that number, my guess is if this is written well, every time you ask array for the size, it doesn't count the number of items. It simply has already saved this number the last time somebody put something in it. So this line returns you the value of n, but it's not really going to count the number of items again and return that number. Does that make sense?
So it just returns you the value of the amount of buckets
Yeah,
you
it
have?
just returns the number of items that are currently in the array.
Okay.
John, I saw your
would
hand
be
come up
O1.
a second ago.
So,
Yeah, that would be big O1, that's correct. How about the constructor up here? What does it run in? So yeah,
This one runs in big O n because
why is that?
The statement inside the for loop runs size number of times in order to initialize every single element of the array to null. So
Very good. Yes, exactly. That's exactly right. This line here also runs, some pieces of it run almost n times. This guy, of course, only runs once. But yeah, because we have to do this, we wind up running n time. We go n time. Do you have any questions about how we calculated any of those?